everyone, I welcome you all to this digital classroom for the subject control systems. Today let us solve one example problem which has been taken from the model question paper which has been released by VTU, subjected to module 5 state space analysis. You can take down this question. Obtain the state equation for the electrical network shown in figure. You have been given with an electrical network and we have to obtain the state equation for the electrical network. So you know to represent the state equation. The state equation is given by the first derivative of the state variables x1 dot, x2 dot and so on, which will be equal to a multiplied by the state variables x1, x2 based upon how many state variables you get for an electrical network plus matrix B multiplied by U. U is nothing but the input. x1, x2, x3 and so on are the state variables, and the first derivative of the state variable can be represented by x1 dot, x2 dot and so on. And in general we can represent it as x dot bar is equal to a into x bar plus b into u. So for a given electrical network, the number of energy storing element will be equal to the number of state variable. So the first step is to identify the number of state variable from the given electrical network. So based upon the number of energy storing element, we get the number of state variables. I will repeat you once again. First step is to identify the number of energy storing element, and the number of energy storing element will be equal to the number of state variable. In this example, we have two inductor L1, L2 and one capacitor C1. So here in this case, we have three energy storing element. So we will be having three state variable. Let me write here number of energy storing element will be equal to number of state variables. As we have here three energy storing element, two inductor and a capacitor. In this case, we have three state variables. And always we have to choose voltage across the capacitor. Here we have a capacitor and the voltage across the capacitor, let us represent it as VC. And we have to consider for the current flowing through the inductor as the state variables. So we have to choose the voltage across the capacitor and current flowing through the inductor as the state variable. So the first state variable is VC. We have three state variables. The current flowing through the inductor is I1 of t and the current flowing through this inductor L2 is I2 of t. And the voltage across the capacitor is VC. Hence, we have three state variables I1, I2 and VC. Always we have to consider for current flowing through the inductor and the voltage across the capacitor. This has to be taken into consideration. Then we have to write the state equation in vector matrix form. And also we have to write the output equation by taking the voltage V0 across the resistor R2. Once after identifying the number of state variables as 3, and once after representing the current flowing through the inductor and the voltage across the capacitor as the state variables I1, I2, VC. Now let me represent these three state variables in terms of the general representation of the state variable as x1, x2 and so on. So I can write it as x1 is equal to I1 equation number 1, x2 is equal to I2, equation number 2, x3 is equal to VC, equation number 3. Just I have represented the state variable in terms of x1, x2, x3, general representation of a state variable. Now let us differentiate equation number 1, 2 and 3. If I differentiate x1, that is dx1 by dt, that becomes the first derivative of the state variable, that is nothing but x1 dot and x2 dot. That is what required for representing the state equation. So if I differentiate equation number 1, x1 dot will be equal to I1 dot, that is nothing but di1 divided by dt. Let me number it as equation number 4. Differentiating equation number 2, differentiation of x2, the first derivative, x2 dot will be equal to I2 dot, that is nothing but di2 divided by dt. Let me number it as equation number 5. For the third equation, if I differentiate the third equation, x3 dot will be equal to vc dot, that is dvc divided by dt. This is by differentiating equation number 1, 2 and 3. Once after differentiating equation number 1, 2 and 3, now we have obtained the expression in terms of the derivative of the state variable x1, x2, x3 as x1 dot, x2 dot and x3 dot, which is required to represent the state equation. Now let us write the loop equation making use of KVL. At loop 1, the applied voltage is represented as Vi of t, which is equal to R1 I1 of t. So I can write it as R1 I1 plus L1 into di1 by dt, L1 into di1 by dt plus, we have a capacitor here, and look into the current flowing through the capacitor. We have I1 as well as I2. So here I can write it as 1 by C into integral, look into the direction of the current flow, I1 and I2 opposite direction. So I1 minus I2 dt. 1 by C of integral I1 minus I2 of dt. If you look into this equation, we have here di1 by dt, that is nothing but I1 dot, which is the required first derivative of the first state variable, so that we can represent the state transition matrix. So from this equation, we are supposed to extract for I1 dot, that is nothing but di1 by dt. And the reason is we are going to represent the first derivative of the state variable, and we are going to represent the state equation. So the required data is x1 dot. x1 dot is nothing but I1 dot, that is di1 by dt. So I have to extract di1 by dt from this expression. And in the meantime, if you look into the right hand side, all the terms has to be expressed in terms of the state variables. So if you look into the rest of the equation, we have the input Vi of t, that is nothing but here related to this input u, and we have one state variable I1. I1 is nothing but x1, which can be represented here as x1. Then we have a term here 1 by C of integral I1 minus I2 dt. So as we have to represent the right hand side in terms of the state variable, now I have to represent the term 1 by C integral I1 minus I2 dt in terms of the state variable. So only possibility here is to represent the voltage across the capacitor here is Vc. Hence, I can represent 1 by C integral I1 minus I2 of dt as Vc. The reason is, to obtain the state equation, the left hand side should be of the form of the first derivative of the state variable, and it has to be represented only in terms of the state variable x1, x2, x3 and so on. Whereas in this case we have the state variable as I1, I2 and Vc. So the first derivative here x1 dot is I1 dot. So if you extract I1 dot, the rest of the terms should be represented in terms of the state variables only. And that is the reason why 1 by c of integral I1 minus I2 dt has to be replaced by Vc, that is the voltage across the capacitor, which is nothing but the state variable. So always remember, once after writing the loop equation, it is always mandatory to transform this term in terms of the state variable. So now let me rewrite the expression as Vi of t is equal to R1 I1 plus L1 di1 by dt plus Vc. Now let me rewrite the equation once again as L1 di1 by dt is equal to Vi of t minus R1 I1 minus Vc. L1 di1 by dt, I can write it as I1 dot is equal to 1 by L1 Vi of t minus R1 by L1 I1 minus 1 by L1 into Vc. Okay, just I have taken L1 towards the right side. So 1 by L1 of Vi of t minus R1 by L1 into I1 minus 1 by L1 into Vc. So now we have I1 dot. That is the first derivative of the state variable I1. So now it has to be represented in terms of the state variables. So let us arrange in terms of the state variables. So I1 dot is equal to minus R1 divided by L1 into I1. That is the first variable, state variable x1, where x1 is I1. So I have written here as I1. Minus, I don't have any second state variable I2 here. So I can write it as 0 into I2 minus 1 by L1 into Vc, the third state variable Vc. Plus, then we have the input term here, 1 by L1 of Vi of t. So we have obtained the first derivative of the state variable I1 dot. Let me number this equation as equation number A. Now, at loop 2, let me consider it as voltage across a capacitor. Anyhow, if we write the expression as 1 by c into integral of I2 minus I1 of dt, again you are going to replace it by Vc. Therefore, we can write it directly now onwards that Vc, the voltage across the capacitor Vc for loop 2 equation, will be equal to L2 into current flowing through the inductor is I2. So di2 by dt plus R2, we have a resistor here R2 and current flowing through the resistor is I2. So R2 I2. So from this equation, now we have the from this equation, we have the first derivative of the second state variable I2 dot, that is di2 by dt. So let us represent di2 by dt, and in the right hand side it has to be in terms of the state variables I1, I2 and Vc, remember. So now L2 di2 by dt is given by Vc minus R2 I2. Hence I can write I2 dot is, taking L2 towards the right side, minus, the first term I don't have any I1 term, so 0 into I1 minus R2 we have here, L2 taken to the right side, R2 by L2 into I2 plus 1 by L2 into Vc plus 0 into Vi. 0 into Vi. And let me number this as equation number B. So now we have obtained the first derivative of the first state variable I1 and the first derivative of the second variable I2. Now the left out thing is to find the first derivative of the third state variable Vc, that is Vc dot. We know that Vc is equal to 1 by C integral I1 minus I2 into dt. This we have obtained from the expression 1 by C into integral I1 minus I2 dt can be written as Vc. So I have taken this expression and I have represented Vc as 1 by C into integral I1 minus I2 into dt. And this is the only way to represent the state variable Vc. But our point of interest is to find the first derivative, that is Vc dot. So let us differentiate the above equation. So differentiating the above equation, Vc dot is equal to, so we have a differentiation and integration, it get cancelled out. dVc by dt will be equal to 1 by C of integration and differentiation will get cancelled out. I1 minus 1 by C of I2. So now let us represent the first derivative of the third state variable in terms of the state variables I1, I2, Vc with respect to the input also. So 1 by C into I1 minus 1 by C into I2, and we don't have any state variable Vc here, so 0 into Vc, and input is also not available, so 0 into Vi. This I can number it as equation number C. So making use of equation number A, B and C, now we have to represent it in a form of a matrix. Let me rewrite again equation number A and B here in this sheet. I1 dot is equal to minus R1 by L1 I1 minus 0 I2 minus 1 by L1 Vc plus 1 by L1 Vi. And I2 dot is given by 0 I1 minus R2 L2 into I2 plus Vc plus 0 into Vi. Equation number A, equation number B, and now we have obtained for equation number C as Vc dot is equal to 1 by C into I1 minus 1 by C into I2 plus 0 into Vc plus 0 into Vi. Equation number C. Now making use of A, B and C, let us represent in the form of a vector matrix. I1 dot, I2 dot and Vc dot is equal to, remember it has to be represented in terms of the state variable I1, I2 and Vc. So with respect to the first equation number A, coefficient of I1 is minus R1 by L1. So R1 by L1 into I1 plus of, we don't have any coefficients for I2, so that is 0, and coefficient of Vc is minus 1 by L1. So if you wanted to write for the first equation I1 dot, we can multiply with first row and the first row of the first matrix with the first column of the second matrix. So minus R1 L1 into I1, 0 into I2, minus 1 by L1 into Vc. First row of the first matrix multiplied by the first column of the second matrix. Similarly, for I2 dot, coefficient of I1 is 0, coefficient of I2 is minus R2 by L2, which is written here, and the coefficient of Vc is 1 by L2. So with respect to the second equation, we can multiply the second row of the first matrix with the first column of the second matrix to obtain the equation number B. 0 into I1 minus R2 by L2 into I2 plus 1 by L2 into Vc plus 0 into Vi gives you this expression. Similarly, Vc dot can be written as coefficient of I1 is 1 by C has been written here, Coefficient of I2 was minus 1 by C has been written here, and coefficient of VC is 0. So to obtain this equation, we have to multiply the third row of the first matrix with the first column of the second matrix. So 1 by C into I1, the first term, minus 1 by C into I2, we can obtain the second term. 0 into VC, we can obtain the third term, plus 0 into VI. So 0 into VI. Only with respect to equation number A, we have a coefficient of VI as 1 by L1. Rest of all the two equations, we have the coefficient of VI as 0. Now, let us transform the state variable representation of I1, I2 and VC in terms of x1. I1 replaced by x1, I2 replaced by x2 and VC replaced by x3, as well as x1 I1 dot replaced by x1 dot, I2 dot replaced by x2 dot and VC dot replaced by x3 dot. So once after transforming, we will obtain the state equation as x1 dot, x2 dot and x3 dot, which is equal to minus R1 by L1, 0 minus 1 by L1, 0 minus R2 by L2, 1 by L2, 1 by C minus 1 by C, 0, x1, x2, x3 plus 1 by L1, 0, 0 into Vi. And this gives you the state equation. So apart from finding the state equation, this is your state equation. We have to write the output equation also. The output equation is given by, if you look into the circuit diagram, the output we have V naught of T across the resistor R2. So V naught of T is equal to the current flowing through the resistor R2 is I2. So I can write it as R2 into I2. So the output equation V naught of T is equal to R2 into I2. So for the output equation also, let us represent in the standard form. That is, we don't have any I1 terms, so 0 into I1 plus R2 into I2 plus 0 into VC. The reason is, again, the output equation also has to be represented in terms of the state variable I1, I2 and VC. So let us represent in vector matrix form. V0 is equal to 0, R2, 0, I1, I2 and VC. Let us replace I1, I2 and VC by x1, x2 and x3. Hence I can write the expression as 0 R2 0 into x1, x2 and x3. This gives my output equation. Hence, for a given electrical network, we have obtained the state equation as well as the output equation also. In the next lecture, let us solve few more example problems related to this chapter, state space analysis. Thank you.